Today's video, we're going to continue our discussion of identical particles, which we introduced last video and basically pointed out that in quantum mechanics, when you're treating particles of the same type, say two electrons, um, they are indistinguishable, as in there is no measurement we can make that can tell which particle is which. And this had a lot of repercussions, right? So we approached this and we discussed what we're calling the symmetrization um, postulate, which essentially says if I have a system of particles, they quantum mechanically they have to have a certain symmetry under exchange. So exchange we defined this exchange operator Pij that when it acts on the ket of some system of particles, it essentially just exchanges, particle I with particle J. That's what the operation does. And under exchange, that system gives us an eigenvalue equation with one of two eigenvalues, either plus or minus one. If the eigenvalue is plus one, that system is symmetric under exchange. And if it's minus one, so plus one eigenvalue is that, minus one eigenvalue, it is anti-symmetric. And it turns out that this sort of property of the system is correlated with the type of spin the particles have. If the particles have integer spin values, they're symmetric and what we call bosons. And if they're half integer spin, then they are anti-symmetric under exchange and what we call fermions. And that property alone leads to a lot of things. One of the important things we have to realize when we're thinking about the symmetrization postulate is that this exchange operator acts on the full state ket. So that state ket has to include a spatial part that we typically think of as sort of the wave function of that system, in position space, and a spin part, which has to do with that spin angular momentum of all the particles in that system, right? So, for example, if we're looking at bosons, the spatial and the spin part can both have asymmetry under exchange. And if we're looking at bosons, the total state ket has to be symmetric under exchange, which means the spatial and the spin part have to have the same type of symmetry for bosons. So for bosons, if they're both anti-symmetric, well, that means I'm going to get a -1 when I exchange the spatial part and a -1 when I get the spin part. So the whole ket would be +1 eigenvalue. Or likewise, if they were both symmetric, I would get a +1 eigenvalue again. So that's what we get for bosons. If we were looking at fermions, we would have the opposite. They would have to have different symmetries. So if the spatial part was anti-symmetric, the spin part would have to be symmetric, and vice versa to get that -1. So that led to some very interesting properties. One important one that we focused on a bit was for the case of, say, fermions. If we had a symmetric spin state, which but you have to, for example, what we looked at was a system of two particles. If they have the spin state, if the two particles have the same spin state, then the combination of them has to be symmetric, because if you exchange the two, you get the same thing back. So that meant if we have two spin particles in the same spin states, the spatial wave function has to be anti-symmetric, which had serious repercussions when you looked at the probability density of where you would find those two particles. For example, if we look at this figure that we focused on at the end of last time's lecture, what we were looking at was the probability densities. We were looking at the first excited state of a two system of two spin 1/2 particles in a infinite well. but the point I wanted to make is we had the probability density from a symmetric spatial wave function and an anti-symmetric spatial wave function. And if you'll notice, both of these probability densities are symmetric about that x1 equals x2 line, right? If we plot, so that's essentially the probability density of that line is telling us the probability of finding both particles at the same location at whatever location that is. And you'll notice if we have the symmetric if we have a symmetric spatial wave function, there is a possibility, and a pretty big one if, in this case, of finding those particles at the same location, right? Whereas in the anti-symmetric spatial wave function, they're kind of pushed apart. There is no chance that they will be found rather at the same location. And this anti-symmetric wave function is what has to be the case if we have a symmetric spin state, which means if my two spins are in the same spin state, there is no way that they can exist at the same location. And that's essentially Pauli exclusion. So all because of this exchange symmetrization postulate, we have this sort of tendency where fermions that tend to push apart from each other, right? Like the probability of them being found in the same location uh, goes down. It's essentially zero if they're in the same states. Whereas for bosons, they tend to sort of be attracted and cluster together. This is an apparent interaction we call the exchange interaction. And it's a bit different from, say the Coulomb interaction or other interactions we've looked at in the sense that it's not some fundamental field or interaction between the particles. It's an apparent interaction that arises purely from the requirement of the state function to be symmetric, have a certain symmetry under exchange of those particles. So that's what we looked at last video. In today's video, we're going to start to look at including other interactions between the particles and things like that. If you recall, we started this whole discussion last video of basically making our Hamiltonian just the Hamiltonian had the two particles existing in some potential, but there was no part of that potential was due to an interaction between the two particles. We're going to today look at including that term. So how do we do that, right? Let's take our two particle system and say that those two particles interact, and there's some interaction between them that just depends on the separation of those two particles. And we'll further assume that there's no spin interactions here. We're not looking at anything like that. And what we can do is we can essentially treat this as a perturbation on the system we looked at before. So if we're looking at our simple two particle system in one dimension, and we look at that boson case where S1 was equal to 0 and S2 was equal to 0. So the spin state for symmetric, well, the only spin state we can have really is both of them in that 0, 0 state. If we wanted to figure out, say, the ground state, how that interaction affects the ground state energy, well, we would look at what that ground state, the first order energy correction is, which is just the diagonal matrix element of that perturbation. And again, this is the full wave state function. So it's got the spin and the spatial part of it like this. But as we said, since this Hamiltonian, our perturbation Hamiltonian, is acting only on the spatial part, this is just going to be the spatial wave functions, that matrix element. And then the spin parts would essentially just normalized. They just go away because that 0, 0 state is normalized. So then we just have to figure out what this matrix element is to get our energy shift. And to do that, that is we just go to the position representation and do the integral that we would do for that, which gives us uh, the remember we're looking at the symmetric ground state of the spatial wave function, which is just going to be um, psi1 at x1, psi1 at x2 times that v of x1 minus x2, and then psi1 at x1, psi1 at x2, integrated over all space for both those positions. Um, or this is what we call the direct integral. And it can more generally be written as we would call it J and M. In one dimension, it would be the integral from negative infinity to infinity, negative infinity to infinity of, excuse me, that nth state at x1 squared v x1 minus x2 and the mth state at x2 squared dx1 dx2. So this is the more general way of writing the direct integral. And if we get that, we call it J and M. That tells us that the ground state to first order is going to be 2E1 plus the result of that direct integral J1, where if you remember the E1, this is our unperturbed state. It's essentially, we have two particles, both in the n equals 1 ground state. So we have 2E n equals 1 energies, and then the perturbation from the direct integral. If we look at fermions, our simple fermion thing, we get the exact same thing. So this is the same thing for the ground state of two fermions. The only difference from this whole thing would be we'd be looking at a different spin state, but it comes out anyway. We'd be looking at that spin singlet where it's the combination of a spin up and spin down fermions, if they were spin 1/2 particles, that anti-symmetric combination of those two. But that's how we can look at it for the ground state. Now, if we look at the excited state, well, the ground state was just those, both particles in that n equal 1, single particle ground state. The first excited state is going to have one of the particles, we'll call it Na in state 1, and another particle in state 2. But what that means is we still have to have symmetric and anti-symmetric combinations of these. We can't say one particle in one in the other. So we're going to have the spatial part of the wave function be either symmetric, in which case it's equal to 1 over root 2 psi 1 at x1, 2 at x2, plus 1 at x2, and 2 at x1. And the anti-symmetric combination of those two is the exact same thing, except for we just have a minus sign in the middle, where this is minus those two. So we have both options in this case. In the ground state, where both particles were in that n equals 1 state, this anti-symmetric, you couldn't form an anti-symmetric state because you'd basically get 0 because they would subtract. In the first excited state, we have both options, right? So when we consider that perturbation again, that perturbation from the two particles interacting and figuring out the energy shift due to it, we're still going to be looking for that first order energy shift, and it's just going to be that spatial part because the spin parts come out, but it's going to be either the antisymmetric wave matrix element or the symmetric wave function element. But either one of those is sort of what we're doing. So if we're looking at, let's start with the boson case and stick with our 0, 0 spin states, which means the spatial part of the wave function would have to be symmetric. We can calculate this matrix element, again, just in the position representation, doing those integrals from negative infinity to infinity of those wave functions. We end up with 1 over root 2, 1x1, 2x2 plus 1x1, 2. Oh, that's x2, sorry. x1 v x1 minus x2, that perturbation potential. It's 1 over root 2, 1 x1. These are all, sorry, complex conjugates, my bad. Plus and then integrated over both the position variables, right? And if we look at this, what we see is when we actually carry out this integral, we get 4 terms, right? This times that one, and this with that one and that one. But they're kind of pairwise the same, right? So we get a 1/2 from these two constants out front, but then this first term with this term are going to be the same. So you add them together and it gets rid of the 2. This whole thing sort of simplifies to 2 integrals. And the first order energy correction can be written as the first one is actually the direct integral, the same thing we had above for the ground state where we integrate from negative infinity to infinity of psi1 x1 squared v x1 minus x2 psi2 x2 squared dx1 dx2. So that's the direct integral we had before. And the other integral we get is integrated over all space again for both our position variables, but it's going to be psi1 star x1 complex conjugates of those, which be x1 minus x2 dx1 dx2. And we call this integral we call this the exchange integral. So this is the exchange integral. And we can write it more generally as k n m, and it's going to be integral negative infinity that. So if we're looking at the total shift of this first excited state, remember, we can call this is our direct integral. If we're looking at it for, let's say, the boson case, where these are the wave functions are the spatial wave functions are symmetric under exchange. This is going to be again, oops, this is 2, 1, 2, is going to be the unperturbed single particle energy levels plus the exchange integral, or sorry, the direct integral for that 1, 2 state, and then plus the exchange integral for that 1, 2 state. That's this k integral right here. And we have that correction. Now, the only real difference when we look at the fermion situation is for the fermion state, is this minus sign. So those cross terms that give us the exchange integral, they're going to have a minus sign in front of it. And what that means is this K12 term is then subtracted instead of added to. So this actually lifts the sort of spin degeneracy in the fermion case. So, and we can see that if we look at figure 13.6 from the textbook, what it shows is essentially what we've got is, well, in the boson case, sorry, we've got the ground state has just the unperturbed ground state before we take into account that the interaction between the particles has, just two particles in the n=1 state. That's the energy we put on for the symmetric spatial wave function. We get this exchange, or sorry, this direct integral to J11 that raises and shifts that energy up to the perturbed energy level. In the first excited state, we've got an unperturbed energy of just E1 plus E2. The direct integral J12 raises the energy to that level, and then because we're in the we're looking at a symmetric spatial state, we have the plus sign here, and the exchange integral raises that energy further rather. In the fermion state, we have again, the ground state looks very similar. We have the J11 that shifts the energy up. But in the excited state, we get something different. Remember, we have 4 degenerate spin states here, and when we get that direct integral stays the same and shifts it up, but that exchange integral, if we're in the anti-symmetric spin singlet state, we must be in the symmetric spatial state, which means we're in the plus K12 integral. So we raise that energy up by K12. If we're in the the symmetric triplet spin states, that means we're in the anti-symmetric spatial states. So that is minus that exchange integral, and we've lowered the energy by that K12. So we've split that spin degeneracy due to the exchange interaction. What we're going to do next is, and sort of to finish off the semester really, is look at an example of this where we're going to put in an actual perturbation, actual Hamiltonian in that, and consider helium. We're going to consider the helium atom, right? So this is just 2 electrons and 2 protons. And if we think about the Hamiltonian for that system of those 2 electrons, we have a Hamiltonian that looks like this. We've got the kinetic energy of the 1 electron, p squared plus 2m, minus the potential energy, or the electrostatic energy of it interacting with the 2 protons in the nucleus, R1. Then we've got the kinetic energy of the second electron and its potential energy of interacting with those 2 protons at the nucleus, R2. And then we've got this repulsive electron-electron interaction where those 2 electrons are interacting with each other. So if we look at this, we've got the nucleus here, which is just all right as He++, are where the 2 protons are. We've got electron 1 somewhere over here at the vector R1. We've got the other electron. It's going to have some position variable or vector R2, and then we've got the sort of vector separating those 2 electrons R1, 2. So we've got the attractive, just to separate these down, we've got kinetic energy of particle 1 and particle 2, of electron 1 and electron 2. We've got the attractive potential energy between the 2 protons that form the nucleus and the 1 electron. The same thing for the other electron. And then we've got this repulsive potential energy from the 2 electrons sort of repelling each other with that Coulomb interaction. And what we're going to do is we're going to treat this term as our perturbation. So, and this is essentially H1 plus H2 plus this perturbation, where, we know the solutions of these two non-interacting Hamiltonians, just like we did before. They're going to be the hydrogenic wave functions that we derived way back in chapter 8, right? So if you think about this H1 Hamiltonian, we know that the eigenstates for that Hamiltonian are just going to be the NLM R theta phi hydrogen wave functions. But we're going to do that, in this case, we're not going to set that nuclear charge. That Z is going to be equal to 2 in this case, which we got 2 electrons there. That scales the energies and all sorts of things. But this allows us, we now know what's going to make up our spatial wave functions are going to be symmetric and antisymmetric combinations of those two, of two of those hydrogenic wave functions. And the energy of our unperturbed system is essentially, well, it's going to depend on the NLMs of the two different um, electrons. So a lot of subscripts here, NLM of particle A, NLM of particle B, and it's going to be, the negative Z squared times the Rydberg 1 over NA squared plus 1 over NB squared. So with our n equals 2, this ends up being just negative 4 Rydbergs times 1 over NA squared plus 1 over NB squared. So this is sort of the system we're looking at for helium, and the spatial wave functions, the states that we're concerned with. Well, we have the symmetric wave function, and again, forgive the time it takes me to write all the subscripts here. That wave function, which is going to depend on those two vectors, R1 and R2, is 1 over root 2, and it's just going to be the symmetric combination of psi NA, LA, MA, R1, where this is the full vector in spherical coordinates, and B, L, B, M, B, R2. And the symmetric combination is plus the other variables at the other position things. B, L, B, M, B, R1. And then the anti-symmetric version of that, R1, R2, is the exact same thing, 1 over root 2, except for a minus sign here. So I'm just going to save us all some time and put those down here. And same thing for the subscripts there. So that's the system we're looking at. We're looking at 2 electrons on this. So the spin, so that's the spatial part of the state function. The spin part, well, we have, in the coupled bases, we have the 1, 1, the 1, 0, the 1, -1, and the 0, 0 states, which are just, this is the plus plus. If we write it in the uncoupled basis, this is 1 over root 2 plus minus plus minus plus, and this is minus minus, and this is the singlet state, which is plus minus 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 plus. So these top 3 states are symmetric spin states that we call the triplet states. Hopefully we're familiar with them now. And this 4th one is the anti-symmetric. And it's the singlet state. So that's what we're set up. The possible, these electrons have to be anti-symmetric under exchange. So that means the 2 possible wave functions or state functions we can have is symmetric, spatial, anti-symmetric, spin. And again, it's going to depend on all of those subscripts, those spatial quantum numbers. And that's going to be equal to, forgive me, I'm just going to write symmetric NLM and LM. And then one of those anti-symmetric, which only gives us the zero spin state, or we can have the anti-symmetric spatial and symmetric spin states, NLM and LM. Which gives us the anti-symmetric spatial state, NLM. With one of those triplet states, which can have m equal to 1, 0, or -1. So these are the symmetric, or the possible combinations of our of state functions we can have, either symmetric spatial and anti-symmetric spin, or vice versa. And now what we're going to do is essentially do what we just did for our one-dimensional example and apply this perturbation Hamiltonian, the interaction between those two electrons, to these states, and see how it works out to be, kind of a specific case of what we just went through. We can start by looking at the ground state, right? So if we're looking at the ground state, we already know that it's only going to depend on the spatial, this n part, these n values of our wave functions in the spatial state. And so essentially we're looking at both particles in the n equals 1 state, which means that Lm for both of them are 0, for both L sub A and L sub B and M sub A and M sub B. But this also means that we have to have a symmetric spatial part. So our spin state in our ground configuration is going to be that singlet. But going back to our energy of that state, we know that it's going to be -4 Rydbergs times 1 over 1 squared plus 1 over 1 squared, which ends up being equal to -108.8 eV. Now, if you recall, when we were looking at those hydrogenic wave functions, our zero, our energy equal to 0, was referenced as when the electron was away from the nucleus at infinity. So that -108 eV is actually describing what we would call the double ionization energy. It's the energy where we've taken both electrons and taken them out to infinity. So that's way up here. That's the zero state. The way we're calculating it is referring to both electrons out at infinity. What we realize, if we just look at the spectrum from the way we calculate this energy of Na plus 1 over Na squared plus 1 over Nb squared, what we notice is there is a single ionization energy. So if we take Nb, say, and set it to infinity, we get this energy here, which ends up being, if we look at E1 and infinity, we end up with -4 Rydbergs 1 over 1 squared plus 1 over infinity squared. This ends up being -54.4 eV. And so that gives us this energy level. If we look at any sort of doubly excited states where both Na and Nb in helium are above the n equals 1 state, those energies are much higher than this, what we would call the single, or just the ionization energy. So that means if we were to be excited to one of these states, there's a chance, and a really good chance, that it's going to quickly decay to this one and just fall to the ionized state. So what's typical is to sort of reset our energy scale and set the 0 to this single ionization energy here. And to do that, we just basically have to shift all our energy levels by that negative amount there. So ultimately, that's what we're going to end up doing, and referencing everything to those single ionization energies. In literature, and that it's typical to do this, and it essentially means when you're looking at the states of atoms, and that you're referring to all the electrons in their lowest energy configuration, except for possibly one of those electrons being excited to higher energy states, like this, where one of the electrons is in the n equals 2, or the n equals 3, or the n equals 4 states. Um, so yeah, that's how we're going to deal with the energies. Now, what we want to do now is, again, this is our unperturbed sort of energy. We want to add the perturbation from that electron-electron interaction, that essentially E squared over 4 pi epsilon naught R1 minus R2 perturbation Hamiltonian. And we're going to add that to our, we're going to deal with perturbation theory, or apply perturbation theory to the helium atom using that. Now, for the ground state of helium, where we have both that and that they're both electrons are in those 1s states, that's a non-degenerate state. There's only the spin singlet is the only anti-symmetric spin state we can have, and all we can have is the symmetric spatial state. So the non-degenerate perturbation theory basically just says that energy shift to that 1s ground state is, again, that diagonal matrix element, where we're looking at symmetric spin, or spatial and anti-symmetric spin in the 1s states of that perturbation. 1s, and again, this ends up being equal to, we can just look at that 1s, the symmetric spatial part. That Hamiltonian is only involved in the spatial part, so we're looking for that matrix element, and we have the 0, 0, 0, 0 spin part, anti-symmetric spin part, that just goes to 1. So the energy shift ends up being that just that symmetric E squared over 4 pi epsilon naught R1 minus R2 matrix element. That, again, we have to calculate. We do that integral. It ends up being, the integral of the 1, 0, 0 hydrogenic wave function at x1, or R1, sorry, that vector R1, 0, 0 at R2, E squared over 4 pi epsilon naught R1 R2. That R2 and R1. And that's integrated over the volume, all of space for R1 and all space for R2, but we're in 3 dimensions. Now, this is the direct integral. This is the 3-dimensional version of the direct integral that we had before, right? So generally this can be written as J N L N prime L prime. I'm dropping the m's because they don't affect this energy or come into the integral there. And this ends up being, in general, we can write it as the integral psi n L at R1 squared times that potential. So in this case, E squared over 4 pi epsilon naught R1 minus R2. And then the probability density of the other state at R2 squared, and then again integrated over all space. So this is our direct integral in the helium atom, and conceptually this makes sense, right? This comes from the electron-electron Coulomb interaction, and if you think about what this integral sort of means, is, well, this integrating this overall space is the probability that the electron in that state is at that R1 position. This is the probability density that the electron in that state is at that position. And if you multiply that by the energy, so the Coulomb interaction energy associated with if there were two electrons at those two locations, if you integrate over all space, you're getting the energy associated with two electrons being in those two states. So I think this sort of Coulomb repulsion interaction, this is why they call it the direct integral, is just you're taking the direct Coulomb interaction between those two electrons at those two locations. Now, this integral is pretty hard to do. In general, it takes advantage of something in spherical harmonics, where you can write this R1 minus R2 as the sum over L is equal to 0 all the way up to infinity, and M equal to negative L to L of 4 pi over 2L plus 1 R less than to the power of L and R greater than to the power of L plus 1, Y LM complex conjugate of that at theta 1 phi 1, and Y L M at theta 2 phi 2. So this sort of identity that comes from the addition theorem of spherical harmonics, we're not going to go through it and all that. You can put that in here. You can use that to replace this term in that integral and actually evaluate the integrals. This R less than or greater than, essentially R less than is whichever one of these R1 or R2 is smaller, and R greater than is whichever one's greater than of those two. But anyway, you can plug that in, and what that gives you when you do that integral is that it gives us that ground state energy shift of E1s 1s. That first order energy shift ends up being 5 over 8 z, which is 2 e squared over 4 pi epsilon naught a naught, that Bohr radius. And if you plug in numbers numerically, you get 34 eV. Makes sense that it's positive. You have that repulsive potential. The electrons are repelling each other, so it's going to increase the energy. And the total ground state energy is going to be, the unperturbed ground state, which is just, excuse me, E1s, 1s to 0th order, plus that 1s first order correction. And if we plug in the numbers before and reference to the single ionization energy, this is negative 54 eV, plus that 34 eV, it's actually 54.4. This ends up being equal to negative 20.4 eV. The experimental value is 25, negative 25. This is close. There's shielding from, the fact that the electrons won't see the full sort of experience or feel the full charge from the nucleus, because the other electron kind of shields it, and that there are other things that come in there, but it gives us, a good, reasonably accurate calculation of the ground state energy, including that interaction for helium's ground state. If we turn to the first excited state, that's going to come from the one electron in the n equals 1 state, the other in the n equals 2 state. Now, because they are not in the same states, we can have both symmetric and anti-symmetric spatial parts of our wave function, where the symmetric part is going to look like this: A, B, B is going to be the symmetric combination of the 1, 0, 0 at R1 and the 2 LM at R2 plus R1 and 2LM R2. Oh, I forgot to switch those. Um, so we have the symmetric combination of those two, and we can also have the anti-symmetric. I'm going to save some time and just shorthand this, where that's a minus sign in between those two. Right, so we have symmetric and anti-symmetric spatial parts. We have the same spin parts that we can have. We have those three triplet states for the two electron spins that are, these are symmetric spin states, the triplets, and we also have the 0, 0 spin singlet, which is the anti-symmetric singlet spin state. So what this means is for the full state function of that first excited state is actually six-fold degenerate, right? These spatial the wave functions, right? The L and the M. Well, L for the n equals 2 state can be 1 uh, and M equal to 1, 0, minus 1, or L can be equal to 0 with M equal to 0. So that's four different possible states that we can arrange symmetrically. Um, so this is four states, or anti-symmetrically four states. We've got three symmetric spin states. So for each one of these anti-symmetric um, spatial wave functions, we can pair that with any three of these. So that's 12 different states. And then we've got these four symmetric spatial parts that can be paired with this anti-symmetric part. So this is 16-fold degenerate uh, in our um, unperturbed, I guess, bases here, right? So we're going to have to use degenerate perturbation theory and essentially diagonalize that subspace for our perturbation Hamiltonian of 4 pi epsilon naught R1 minus R2. Fortunately, this is actually diagonal in this basis, in this 16-fold basis. We're not going to show that, but we can kind of justify it. If you think about it, this interaction, this Coulomb interaction that's causing our perturbation, is an internal perturbation to the system, right? So it can't think about it as it's not, it doesn't involve an external torque on the system or anything, so it's not going to be able to change the angular momentum of that system. So the angular momentum quantum number is still a good quantum number. Um, so that L and those M's are still good quantum numbers. So you can kind of make that just a physical intuitive argument that this is diagonal in our bases. But anyway, those shifts that we're going to find are just going to be the matrix elements of that, the diagonal matrix elements of that perturbation Hamiltonian, where that can be the symmetric, anti-symmetric, spatial symmetric spin form of that 1s 2l state, or also the diagonal symmetric, anti-symmetric combinations of the spin and spatial states, parts of that state. And those that's how we figure out that the first order energy shifts to those states. Just like we saw previously in our little one-dimensional arbitrary interaction example, we can figure this out doing our integration, and we essentially get the integral 1 over root 2 of that psi 1, 0, 0 at R1 to LM R2 plus or minus, depending on whether we're looking at the symmetric or anti-symmetric spin part, over that perturbation potential. And integrated over all space for those two position. Um, so we did this integral, and that gives us our first order corrections, just like we saw before. This is going to have four terms involved in it, two from that one, two from this one. But some of them, they're going to pair up and be equal and sort of cancel what'll be the 1/2 out in front. So putting that all together, we end up with, as we would expect, that this becomes two integrals that we can write as psi 1, 0, 0, R1, that probability density squared, E squared over 4 pi epsilon naught R1 minus R2, and 2LM R2 squared integrated over all space for those two position things. And then we're going to have, again, the plus or minus, depending on if we're looking at the symmetric or anti-symmetric spatial part, our exchange integral, which is going to be 0, R1. Now, again, this is just equal to, this first one is our, it's the 3D analytes, that 1 S2 L a direct integral, and it's plus or minus that 1s 2L exchange integral. And that's the first order shift to that, the, excuse me, first excited state in helium, where the plus or minus refers to plus if we're looking at a state where the first excited state with symmetric parts, spatial part of the state function, and the minus refers to if we're looking at an anti-symmetric part of the wave function. We can see this sort of the whole idea here in figure 13.9, I believe, where what we're looking at is we have sort of those unperturbed ground states, but where before we took in the interaction. One is the ground state that we looked at was the 1s state, and it has two electrons in it. And then when we did the perturbation from the interaction, we did that integral, and all we had was that J 1s direct integral that increased the energy up to here, where this notation is n, giving the principal quantum number, and 2s plus 1 over L, whatever that L state is, SPDF, the type of orbital. But anyway, this direct integral increased the energy of that state. Basically, we include that Coulomb repulsion between the electrons that pushes them apart. And this ground state was that -4 Rydberg's 1 over 1 squared plus 1 over 1 squared, because both electrons are in that n equals 1 state. For the first excited state, well, we have that it's at that -4 Rydberg 1 over 1 squared plus 1 over 2 squared state, because we have one electron in the n equals 1 and one in the n equals 2 state. We include that electron-electron interaction perturbation, and we see that the states that are the 1s, 2s state that was degenerate gets raised, that energy, by the direct integral for the 1s, 2s state. The 1s, 2p states get raised to the 1s, 2p by that direct integral for the 1s and 2p states. But then we also have the exchange integral, that comes into play, and that splits the degeneracy of those two states, right? And it splits them up or down by the appropriate exchange integral. Um, and we get this, where we have this state where this is the spin, the s equals 0 state, and this is the s equals 1 state. So this um, is the anti-symmetric spin state and the symmetric um, uh, spatial wave function, and this is the anti-symmetric spatial function and symmetric spin states. So this one is still threefold degenerate. Likewise, with these two, this is the symmetric um, spatial state and the anti-symmetric spatial states, and the opposite, obviously, for the spins. And this can sort of make sense, right? We know that the probability density for a symmetric spatial wave function results in there's no possible way that those electrons can exist at the same part. So the symmetric um, sorry the symmetric spatial blah, got tongue tied there. Let me start over. We know that if we have a symmetric spin state, so if we look at the symmetric spin states, these lower ones, we have an anti-symmetric spatial state. So if we have an anti-symmetric spatial state, there is no possibility that those electrons can exist at the same location, right? This, if you think way back to when we first started discussing Pauli exclusion, that was the idea. If the spins were in a symmetric state with respect to spin, they had to be anti-symmetric with respect to space, and that means set x1 equal to x2 or r1 equal to r2 in this case, and that goes to 0. There's no chance that they can exist at the same point. So we're effectively pushing those electrons further apart. So that means this Coulomb repulsion is going to be weaker. It's not going to have raised the energy as much, or it's going to lower it from what it was at after including just that direct integral. Whereas if it's a symmetric spatial wave function, they can exist at the same part. Those electrons are closer together. That's a stronger repulsion. That's going to increase the energy. So we see that sort of increase in energy when it's a symmetric spatial wave function, and a decrease in energy when it's an anti-symmetric wave function. And we get this splitting. Um, and right, so this all makes sense. That's kind of where we're going to end it for the semester. The chapter builds on this logic of taking that symmetrization principle, and essentially it leads to the entire periodic table and the electrical structure and the electron configurations across that periodic table. So we'll discuss more of this in our synchronous sessions. But for now, hopefully you're following this, understanding how essentially symmetrization and the requirement that for fermions, the total state wave function has to be anti-symmetric under exchange, whereas for bosons, it's symmetric under exchange, leads to a lot of different effects. The one we've discussed here is essentially this exchange interaction, and it can and just the various ways it comes into play and shifts in this case the helium spectrum. If you have questions, email me, bring them up in the synchronous sessions. I will see you then.